Part 3 of Chapter 16, Airplane Flying Handbook, FAA-H-8083-3A. This LibriVox recording is in the public domain. Flight Control Malfunction/Failure. Total flap failure. The inability to extend the wing flaps will necessitate a no-flap approach and landing. In light airplanes, a no-flap approach and landing is not particularly difficult or dangerous. However, there are certain factors which must be considered in the execution of this maneuver. A no-flap landing requires substantially more runway than normal. The increase in required landing distance could be as much as 50%. When flying in the traffic pattern with the wing flaps retracted, the airplane must be flown in a relatively nose-high attitude to maintain altitude, as compared to flight with flaps extended. Losing altitude can be more of a problem without the benefit of the drag normally provided by the flaps. A wider, longer traffic pattern may be required in order to avoid the necessity of diving to lose altitude and, consequently, building up excessive airspeed. On final approach, a nose-high attitude can make it difficult to see the runway. This situation, if not anticipated, can result in serious errors in judgment of height and distance. Approaching the runway in a relatively nose-high attitude can also cause the perception that the airplane is close to a stall. This may cause the pilot to lower the nose abruptly and risk touching down on the nose wheel. With flaps retracted and the power reduced for landing, the airplane is slightly less stable in the pitch and roll axes. Without flaps, the airplane will tend to float considerably during round-out. The pilot should avoid the temptation to force the airplane onto the runway at an excessively high speed. Neither should the pilot flare excessively, because, without flaps, this might cause the tail to strike the runway. Asymmetric split flap. An asymmetric split flap situation is one in which one flap deploys or retracts while the other remains in position. The problem is indicated by a pronounced roll toward the wing with the least flap deflection when the wing flaps are extended/retracted. The roll encountered in a split flap situation is countered with opposite aileron. The yaw caused by the additional drag created by the extended flap will require substantial opposite rudder, resulting in a cross-control condition. Almost full aileron may be required to maintain wings level attitude, especially at the reduced airspeed necessary for approach and landing. The pilot, therefore, should not attempt to land with a crosswind from the side of the deployed flap, because the additional roll control required to counteract the crosswind may not be available. The pilot must be aware of the difference in stall speeds between one wing and the other in a split flap situation. The wing with a retracted flap will stall considerably earlier than the wing with the deployed flap. This type of asymmetrical stall will result in an uncontrollable roll in the direction of the stalled, clean wing. If altitude permits, a spin will result. The approach to landing with a split flap condition should be flown at a higher than normal airspeed. The pilot should not risk an asymmetric stall and subsequent loss of control by flaring excessively. Rather, the airplane should be flown onto the runway so that the touchdown occurs at an airspeed consistent with a safe margin above flaps up stall speed. Loss of elevator control. In many airplanes, the elevator is controlled by two cables, a down cable and an up cable. Normally, a break or disconnect in only one of these cables will not result in a total loss of elevator control. In most airplanes, a failed cable results in a partial loss of pitch control. In the failure of the up elevator cable, the down elevator being intact and functional, the control yoke will move aft easily but produce no response. Forward yoke movement, however, beyond the neutral position, produces a nose-down attitude. Conversely, a failure of the down elevator cable, forward movement of the control yoke produces no effect. The pilot will, however, have partial control of pitch attitude with aft movement. When experiencing a loss of up elevator control, the pilot can retain pitch control by applying considerable nose-up trim, pushing the control yoke forward to attain and maintain desired attitude, increasing forward pressure to lower the nose and relaxing forward pressure to raise the nose, releasing forward pressure to flare for landing. When experiencing a loss of down elevator control, the pilot can retain pitch control by applying considerable nose-down trim, pulling the control yoke aft to attain and maintain attitude, releasing back pressure to lower the nose and increasing back pressure to raise the nose, increasing back pressure to flare for landing. Trim mechanisms can be useful in the event of an in-flight primary control failure. For example, if the linkage between the cockpit and the elevator fails in flight, leaving the elevator free to weather vane in the wind, the trim tab can be used to raise or lower the elevator within limits. The trim tabs are not as effective as normal linkage control in conditions such as low airspeed, but they do have some positive effect, usually enough to bring about a safe landing. If an elevator becomes jammed, resulting in total loss of elevator control movement, various combinations of power and flap extension offer a limited amount of pitch control. A successful landing under these conditions, however, is problematical. Landing gear malfunction. Once the pilot has confirmed that the landing gear has, in fact, malfunctioned, and that one or more gear legs refuses to respond to the conventional or alternate methods of gear extension contained in the AFM POH, there are several methods that may be used in attempting to force the gear down. One method is to dive the plane in smooth air only to VNE speed, red line on the airspeed indicator, and, within the limits of safety, execute a rapid pull-up. In normal category airplanes, this procedure will create a 3.8 G load on the structure, in effect making the landing gear weigh 3.8 times normal. In some cases, this may force the landing gear into the down and locked position. This procedure requires a fine touch control and good feel for the airplane. The pilot must avoid exceeding the design stress limits of the airplane while attempting to lower the landing gear. The pilot must also avoid an accelerated stall and possible loss of control while attention is directed to solving the landing gear problem. Another method that has proven useful in some cases is to induce rapid yawing. After stabilizing at or slightly less than maneuvering speed, VA, the pilot should alternately and aggressively apply rudder in one direction and then the other in rapid sequence. The resulting yawing action may cause the landing gear to fall into place. If all efforts to extend the landing gear have failed and a gear-up landing is inevitable, the pilot should select an airport with crash and rescue facilities. The pilot should not hesitate to request that emergency equipment be standing by. When selecting a landing surface, the pilot should consider that a smooth, hard surface runway usually causes less damage than rough, unimproved grass strips. A hard surface does, however, create sparks that can ignite fuel. If the airport is so equipped, the pilot can request that the runway surface be foamed. The pilot should consider burning off excess fuel. This will reduce landing speed and fire potential. If the landing gear malfunction is limited to one main landing gear leg, the pilot should consume as much fuel from that side of the airplane as practicable, thereby reducing the weight of the wing on that side. The reduced weight makes it possible to delay the unsupported wing from contacting the surface during the landing roll until the last possible moment. Reduced impact speeds result in less damage. If only one landing gear fails to extend, the pilot has the option of landing with the available gear legs or landing with all the gear legs retracted. Landing on only one main gear usually causes the plane to veer strongly in the direction of the faulty gear leg after touchdown. If the landing runway is narrow and/or ditches and obstacles line the runway edge, maximum directional control after touchdown is a necessity. In this situation, a landing with all three gear retracted may be the safest course of action. If the pilot elects to land with one main gear retracted and the other main gear and nose gear down and locked, the landing should be made in a nose-high attitude with the wings level. As airspeed decays, the pilot should apply whatever aileron control is necessary to keep the unsupported wing airborne as long as possible. Figure 16-7. Once the wing contacts the surface, the pilot can anticipate a strong yaw in that direction. The pilot must be prepared to use full opposite rudder and aggressive braking to maintain some degree of directional control. When landing with a retracted nose wheel and the main gear extended and locked, the pilot should hold the nose off the ground until almost a full up elevator has been applied. Figure 16-8. The pilot should then release back pressure in such a manner that the nose settles slowly to the surface. Applying and holding full up elevator will result in the nose abruptly dropping to the surface as airspeed decays, possibly resulting in burrowing and/or additional damage. Brake pressure should not be applied during the landing roll unless absolutely necessary to avoid a collision with obstacles. If the landing must be made with only the nose gear extended, the initial contact should be made on the aft fuselage structure with a nose-high attitude. This procedure will help prevent porpoising and/or wheelbarrowing. The pilot should then allow the nose wheel to gradually touch down, using nose wheel steering as necessary for directional control. System malfunctions. Electrical system. The loss of electrical power can deprive the pilot of numerous critical systems, and therefore should not be taken lightly, even in day VFR conditions. Most in-flight failures of the electrical system are located in the generator or alternator. Once the generator or alternator system goes offline, the electrical source in a typical light airplane is a battery. If a warning light or ammeter indicates the probability of an alternator or generator failure in an airplane with only one generating system, however, the pilot may have very little time available from the battery. The rating of the airplane battery provides a clue of how long it may last. With batteries, the higher the amperage load, the less the usable total amperage. Thus, a 25 amp battery could produce 5 amps per hour for 5 hours. But if the load was increased to 10 amps, it might last only 2 hours. A 40 amp load might discharge the battery fully in about 10 or 15 minutes. Much depends on the battery condition at the time of the system failure. If the battery has been in service for a few years, its power may be reduced substantially because of internal resistance. Or, if the system failure was not detected immediately, much of the stored energy may have already been used. It is essential, therefore, that the pilot immediately shed non-essential loads when the generating source fails. Figure 16-9. The pilot should then plan to land at the nearest suitable airport. What constitutes an emergency load following a generating system failure cannot be predetermined, because the actual circumstances will always be somewhat different. For example, whether the flight is VFR or IFR, conducted in day or at night, in clouds or in the clear. Distance to the nearest suitable airport can also be a factor. The pilot should remember that the electrically powered or electrically selected landing gear and flaps will not function properly on the power left in a partially depleted battery. Landing gear and flap motors use up power at rates much greater than most other types of electrical equipment. The result of selecting these motors on a partially depleted battery may well result in an immediate total loss of electrical power. If the pilot should experience a complete in-flight loss of electrical power, the following steps should be taken. Shed all but the most necessary electrically driven equipment. Understand that any loss of electrical power is critical in a small airplane. Notify ATC of the situation immediately. Request radar vectors for a landing at the nearest suitable airport. If landing gear or flaps are electrically controlled or operated, plan the arrival well ahead of time. Expect to make a no-flap landing and anticipate a manual landing gear extension. Pitot-static system. The source of the pressure for operating the airspeed indicator, the vertical speed indicator, and the altimeter is the pitot-static system. The major components of the pitot-static system are the impact pressure chamber and lines, and the static pressure chamber and lines, each of which are subject to total or partial blockage by ice, dirt, and/or other foreign matter. Blockage of the pitot-static system will adversely affect instrument operation. Figure 16-10. Partial static system blockage is insidious in that it may go unrecognized until a critical phase of flight. During takeoff, climb, and level off at cruise altitude, the altimeter, airspeed indicator, and vertical speed indicator may operate normally. No indication of malfunction may be present until the airplane begins a descent. If the static reference system is severely restricted, but not entirely blocked, as the airplane descends, the static reference pressure at the instruments begins to lag behind the actual outside air pressure. While descending, the altimeter may indicate the airplane is higher than actual because the obstruction slows the airflow from the static port to the altimeter. The vertical speed indicator confirms the altimeter's information regarding rate of change, because the reference pressure is not changing at the same rate as the outside air pressure. The airspeed indicator, unable to tell whether it is experiencing more airspeed pitot pressure or less static reference pressure, indicates a higher airspeed than actual. To the pilot, the instruments indicate that the airplane is too high, too fast, and descending at a rate much less than desired. If the pilot levels off and then begins a climb, the altitude indication may still lag. The vertical speed indicator will indicate the airplane is not climbing as fast as actual. The indicated airspeed, however, may begin to decrease at an alarming rate. The least amount of pitch-up attitude may cause the airspeed needle to indicate dangerously near stall speed. Managing a static system malfunction requires that the pilot know and understand the airplane's pitot-static system. If a system malfunction is suspected, the pilot should confirm it by opening the alternate static source. This should be done while the airplane is climbing or descending. If the instrument needles move significantly when that is done, a static pressure problem exists, and the alternate source should be used during the remainder of the flight. Abnormal engine instrument indications. The AFM-POH for the specific airplane contains information that should be followed in the event of any abnormal engine instrument indications. The table on the next page offers generic information on some of the more commonly experienced in-flight abnormal engine instrument indications, their possible causes, and corrective actions. Table 1 is recorded at the end of the audio track. Door opening in flight. In most instances, the occurrence of an inadvertent door opening is not of great concern to the safety of the flight, but rather the pilot's reaction at the moment the incident happens. A door opening in flight may be accompanied by a sudden loud noise, sustained noise level, and possible vibration and buffeting. If a pilot allows himself or herself to become distracted to the point where attention is focused on the open door rather than maintaining control of the airplane, loss of control may result, even though disruption of airflow by the door is minimal. In the event of an inadvertent door opening in flight or on takeoff, the pilot should adhere to the following. Concentrate on flying the airplane, particularly in light single and twin-engine airplanes. A cabin door that opens in flight seldom, if ever, compromises the airplane's ability to fly. There may be some handling effects such as roll and/or yaw, but in most instances, these can be easily overcome. If the door opens after liftoff, do not rush to land. Climb to normal traffic pattern altitude, fly a normal traffic pattern, and make a normal landing. Do not release the seat belt and shoulder harness in an attempt to reach the door. Leave the door alone. Land as soon as practicable, and close the door once safely on the ground. Remember that most doors will not stay wide open. They will usually bang open, then settle partly closed. A slip towards the door may cause it to open wider. A slip away from the door may push it closed. Do not panic. Try to ignore the unfamiliar noise and vibration. Also, do not rush. Attempting to get the airplane on the ground as quickly as possible may result in steep turns at low altitude. Complete all items on the landing checklist. Remember that accidents are almost never caused by an open door. Rather, an open door accident is caused by the pilot's distraction or failure to maintain control of the airplane. Table 1. Text. Malfunction, probable cause, corrective action. Malfunction. Loss of RPM during cruise flight, non-altitude engines, or loss of manifold pressure during cruise flight. Probable cause. Carburetor or induction icing, or air filter clogging. Corrective action. Apply carburetor heat. If dirty filter is suspected and non-filtered air is available, switch selector to unfiltered position. Malfunction. Loss of manifold pressure during cruise flight. Probable cause. Turbocharger failure. Corrective action. Possible exhaust leak. Shut down engine or use lowest practicable power setting. Land as soon as possible. Malfunction. Gain of manifold pressure during cruise flight. Probable cause. Throttle has opened, propeller control has decreased RPM, or improper method of power reduction. Corrective action. Readjust throttle and tighten friction lock. Reduce manifold pressure prior to reducing RPM. Malfunction. High oil temperature. Probable cause. Oil congealed in cooler. Corrective action. Reduce power. Land. Preheat engine. Malfunction. High oil temperature. Probable cause. Inadequate engine cooling. Corrective action. Reduce power. Increase airspeed. Malfunction. High oil temperature. Probable cause. Detonation or pre-ignition. Corrective action. Observe cylinder head temperatures for high reading. Reduce manifold pressure. Enrich mixture. Malfunction. High oil temperature. Probable cause. Forthcoming internal engine failure. Corrective action. Land as soon as possible or feather propeller and stop engine. Malfunction. High oil temperature. Probable cause. Defective thermostatic oil cooler control. Corrective action. Land as soon as possible. Consult maintenance personnel. Malfunction. Low oil temperature. Probable cause. Engine not warmed up to operating temperature. Corrective action. Warm engine in prescribed manner. Malfunction. High oil pressure. Probable cause. Cold oil. Corrective action. Warm engine in prescribed manner. Malfunction. High oil pressure. Probable cause. Possible internal plugging. Corrective action. Reduced power. Land as soon as possible. Malfunction. Low oil pressure. Probable causes. Broken pressure relief valve, insufficient oil, or burned out bearings. Corrective action. Land as soon as possible or feather propeller and stop engine. Malfunction. Fluctuating oil pressure. Probable causes. Low oil supply. Loose oil lines. Defective pressure relief valve. Corrective action. Land as soon as possible or feather propeller and stop engine. Malfunction. High cylinder head temperature. Probable cause. Improper cowl flap adjustment. Corrective action. Adjust cowl flaps. Malfunction. High cylinder head temperature. Probable cause. Insufficient airspeed for cooling. Corrective action. Increase airspeed. Malfunction. High cylinder head temperature. Probable cause. Improper mixture adjustment. Corrective action. Adjust mixture. Malfunction. High cylinder head temperature. Probable cause. Detonation or pre-ignition. Corrective action. Reduce power, enrich mixture, increase cooling airflow. Malfunction. Low cylinder head temperature. Probable cause. Excessive cowl flap opening. Corrective action. Adjust cowl flaps. Malfunction. Low cylinder head temperature. Probable cause. Excessively rich mixture. corrective action, adjust mixture control. Malfunction, low cylinder head temperature, probable cause, extended glides without clearing engine, corrective action, clear engine long enough to keep temperatures at minimum range. Malfunction, ammeter indicating discharge or load meter indicating zero, probable cause, alternator or generator failure, corrective action, shed unnecessary electrical load, land as soon as practicable. Malfunction, surging RPM and overspeeding, probable cause, defective propeller, corrective action, adjust propeller RPM. Malfunction, surging RPM and overspeeding, probable cause, defective engine, corrective action, consult maintenance. Malfunction, surging RPM and overspeeding, probable cause, defective propeller governor, corrective action, adjust propeller control, attempt to restore normal operation. Malfunction, surging RPM and overspeeding, probable cause, defective tachometer, corrective action, consult maintenance. Malfunction, surging RPM and overspeeding, probable cause, improper mixture setting, corrective action, readjust mixture for smooth operation. Malfunction, loss of airspeed in cruise flight with manifold pressure and RPM constant, probable cause, possible loss of one or more cylinders, corrective action, land as soon as possible. Malfunction, rough running engine, probable cause, improper mixture control setting, corrective action, adjust mixture for smooth operation. Malfunction, rough running engine, probable cause, defective ignition or valves, corrective action, consult maintenance personnel. Malfunction, rough running engine, probable cause, detonation or pre-ignition, corrective action, reduce power, enrich mixture, open cowl flaps to reduce cylinder head temp, land as soon as practicable. Malfunction, rough running engine, probable cause, induction air leak or plugged fuel nozzle, fuel injection, corrective action, reduce power, consult maintenance. Malfunction, rough running engine, probable cause, excessive fuel pressure or fuel flow, corrective action, lean mixture control. Malfunction, loss of fuel pressure, probable cause, engine-driven pump failure, corrective action, turn on boost tanks. Malfunction, loss of fuel pressure, probable cause, no fuel, corrective action, switch tanks, turn on fuel. End of Table 1 text. End of Chapter 16, Part 3.